Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll start a new topic, compound stresses. In actual engineering applications, structures will be subjected to a number of loads in different directions. If a body is subjected to loads only in x direction, it is one-dimensional loading. It is only subjected to uniaxial loading. We have dealt number of cases subjected to stress acting only in one direction. Axial loading of a member, whether it's tensile loading or compressive loading. So if the loads acts in only in one direction, you can easily find out the stress induced. If the body is subjected to stresses in two directions, so that means load acting in two directions. So let us say that the loads are acting in x direction and y direction, but no load in z direction. This kind of stresses induced on a body is known as plane state of stress. So loads may act in x direction, y direction, but not in z direction. So this is known as plane state of stress. So in this figure I have shown an element that is a very small part of the body subjected to loads in two different directions. So I have shown the stress. Stress is nothing but the load per unit area. So load is acting in x direction, load is also acting in y direction. Okay, so stress is acting in x direction, stress is acting in y direction, and also it is subjected to shearing stresses. So shear stress in vertical plane, there is a shearing, like forces are acting like this, and also horizontal plane you have shear stresses. So usually that stresses acting say vertical plane will be associated with the equal shear stresses on a mutually perpendicular plane as per theorem of complementary shear stress. So if it acts in a vertical plane, it will be always associated with the shear stresses of equal magnitude on a horizontal plane. That is theorem of complementary shear stress. Now let us consider an element subjected to plane state of stress like this as shown in figure. In such situations, the maximum normal stress will be different from sigma x or sigma y. So we have to find out the maximum normal stress induced and also maximum shear stress induced in the body. So knowing the maximum stress only, we can strengthen the structure. So we should know when the load acts in different directions, we should know what is the maximum stress induced in the body. So maximum stress in such cases will be different from this sigma x or sigma y or tau xy. So we need to find out the maximum normal and shear stress induced, and also we can find out the stresses on a given plane. First we will find out the stress induced on a given plane at any one particular direction. Let us take a direction like this, theta from the vertical, and find out what stress is acting in that direction. So stress acting in any given direction you can find out, and later we will find out what is the maximum normal stress and maximum shear stress acting on this material. So that is important. Maximum normal stress and maximum shear stress is important in design. So when a body is subjected to compound stresses, in this case plane state of stress, stresses acting in x and y directions, it may be only normal stresses or it may involve shear stresses also, but all stresses are in one plane, that is in xy plane. In x direction and y direction, no forces in z direction. Such a case is plane state of stress, and we'll deal such cases in this particular topic. Now let us consider an element, a small element taken from the body which is subjected to loading in x and y direction. So this is the element ABCD is the element which is subjected to forces in x direction and y direction. So stress is acting in x direction, stress is acting in y direction. So both I have shown tensile, it may be compressive or tensile. Okay. And shear stress is also shown, the shear stress is shown as tau xy. Now if you take the y-axis, that is vertical plane, the stress acting is sigma x, normal stress acting is sigma x, and this sigma y will not come into the vertical plane. The effect of sigma y, because sigma y has no component in x direction, so if you take vertical plane, normal stress will be sigma x. If you take a horizontal plane, normal stress is going to be sigma y. Sigma x component will not come in that plane. So if you take a vertical plane, so only sigma x is acting, but shear stress will be there. So we'll see other than this vertical and horizontal planes, so an inclined plane, what will be the normal stress? So we have to find out that normal stress and shearing stress, how much shearing stress is acting along that plane, how much normal stress is acting. Normal stress means the force which is acting normal to that plane, which is trying to break that member. Now let us take a section plane through this element at an inclination theta, and section plane I'll take through point C. That is, for easy calculation purpose, I'll pass the section plane through point C. You can pass the section plane through any point, but for explanation purpose I'll pass the section plane through C. So I'll take a section plane like this with an inclination theta from the vertical. So this is a section plane, CE is the section plane. Okay. Now this makes an inclination theta. Now I'll show only this part of the element. So effect of these forces is to exert a normal force and a shearing force. Okay. So I have shown the element separately. Now let us assume unit thickness perpendicular to the screen. So area of this top face is going to be AB into 1. So the thickness is 1. So top face will have area AB into 1. Like that, this side, this face BC perpendicular to the screen, it is thickness is 1 unit. So the area of this face is going to be BC into 1. Like you can calculate the area of different faces. Now this element I have separated, and the stresses is sigma x here, sigma y, tau xy, tau xy. Now the normal stress, this element will be in equilibrium as a result of the forces transmitted from here. This part will exert a force, and that force I have shown separately, normal force per unit area. This is shear force per unit area. Normal stress means normal force per unit area, and shear stress means shearing force per unit area. So the resultant force may be inclined. So I have shown it as normal stress and shear stress. So as a result of this, these forces, this element will be in equilibrium. So these are the forces acting externally. This is the internal force. This part is exerting so much of force on this small portion of that element to maintain equilibrium. Now I'll take two directions. Normal to this plane, that is extending this, there is a normal. So sigma is acting normal to that plane. So that normal to that plane, this is normal to the plane, and tangential to this plane. So this is tangential to this plane. So I'll take these two directions to resolve all these forces. These are the stresses. Stress multiplied by area will give the forces. Okay. So here I have shown the forces. So these are the stresses. These are the stresses acting on these faces. Now these stresses will induce forces. This is sigma x. Sigma x is acting on this face. Okay. So the area of this face is BC into normal to the screen, the thickness is 1. So BC into 1 is the area of that face. So sigma x, this stress is sigma x into BC into 1, that will give as the force. So instead here I have shown the stress, but here this is force. Sigma x into BC is the force. Similarly, tau xy is the stress, shearing stress acting on that face, and that shearing stress into area of that face will give the force in that particular direction along that face. Similarly, I multiply with the area EB into tau xy, that is tau xy EB, that will give the shearing force on that face, and sigma y into EB will give the normal force on that face. Now after passing the section plane, normal stress is sigma into EC, area of that face. EC is the length multiplied by thickness normal to the screen will give the area of that face. Sigma EC is the force, normal force, and tau EC is the shearing force. Now this angle is theta. Now if you draw a horizontal here, this is 90 and this angle is 90 minus theta, and this is a normal, this is a normal. So when this is 90 minus theta, this angle has to be theta. So you get the angle the normal makes with the horizontal as theta. Similarly, here you can find out this is theta, and it's the same inclination, same section plane with the vertical. So that makes theta. So this tangential plane, this plane is making an inclination theta from the vertical. Now we will resolve all the forces. Now we understood the forces acting on this element. These forces will be keeping the element in equilibrium. These forces induced on this section will be keeping the element in equilibrium. So to maintain the equilibrium of this element, so much forces are induced. So these forces are keeping the element in equilibrium. So you can sum up the forces in any direction and equate to 0. Any direction, x direction, y direction, or whichever direction. Okay. Here for easy calculation purpose, we'll sum up the forces normal to this plane, normal to this section plane, and along the section plane or tangential to this plane. So this direction will resolve the forces. When you resolve in this direction, horizontal force, this horizontal force, the component of that horizontal force, since this angle is theta, sigma x BC into cos theta will be the component normal to that direction. First I will resolve the forces normal to that plane. Okay, in this direction I will resolve. All horizontal force, this horizontal force is making theta with the normal. And again this force will be making same angle theta with the normal, with this direction. So horizontal force component will be that force into cos theta. Cos theta will be the component. And let us take the vertical force. Vertical force, this angle is theta. So this is 90 minus theta. So vertical force, the component is sin theta, cos 90 minus theta or sin theta. So vertical force, the components will be sin theta. So two vertical forces are there, these two vertical force. Those forces component in the normal direction will be sin theta, and horizontal force, the component will be cos theta. And this is acting normal to that plane, so that will, you can directly take the same value. This is acting normal to this plane, so this has no component in the normal direction. Okay, it's 90 degree. The component of that is cos 90, 0. So I'll show it separately here. Now let us sum up the forces normal to the section plane and equal to 0. And this is a normal to the section plane. Now this force sigma x BC, the component is cos theta, sigma x BC cos theta, and there is one more horizontal force, tau xy EB, that's also acting in the horizontal direction. So its component in the normal direction is cos theta, tau xy EB cos theta. Now let us take the vertical forces. Sigma y EB is acting vertically. That component is sin theta, sigma y EB sin theta. And this vertical force, tau xy BC, that's also component is sin theta, tau xy BC sin theta. All these forces which I resolved, the components are acting upward along the plane. So I have taken all that positive, whereas this is acting downward. Okay, so that downward force I'll take minus sigma EC. This is opposite direction, whereas this is acting in a different direction. All of them are acting upward. The components of all these four forces are acting upward. So I have taken all of them plus, and this is acting downward. So minus sigma EC is equal to 0. Now I'll take sigma EC to the left hand side. Sigma EC is equal to, so the rest of this you can take on the other side. So you get this. Now we'll divide this entire equation by EC. So you get sigma, that is stress. Okay, this is force. Now I'll divide the entire equation by EC. You'll get sigma x BC by EC into cos theta, tau xy into EB by EC cos theta, plus sigma y EB by EC into sin theta, plus tau xy BC by EC into sin theta. Now from this triangle, BC by EC is cos theta, adjacent side by hypotenuse, that is cos theta, cos of this angle, and EB by EC is sin theta, opposite side by hypotenuse, it is sin theta. So there are BC by EC, which is cos theta, EB by EC is sin theta. So EB by EC you can replace by sin theta, BC by EC by cos theta. So we'll do that. So this same equation I have written. Now I'll replace BC by EC by cos theta. So you'll get cos square theta here, sigma x cos square theta. EB by EC I'll replace by sin theta. So you get tau xy sin theta cos theta. Again this I'll replace by sin theta. So you get sigma y sin square theta. And BC by EC is cos theta. So tau xy cos theta sin theta. Now cos square theta I'll write it as 1 plus cos 2 theta by 2. So sigma x into 1 plus cos 2 theta by 2 plus I'll take this term next, sin square theta I'll replace 1 minus cos 2 theta by 2. So sigma y into 1 minus cos 2 theta by 2. These two terms are same. This tau xy sin theta cos theta is also tau xy sin theta cos theta. So 2 tau xy sin theta cos theta or cos theta sin theta. Now sigma x by 2 plus sigma y by 2. So the first term here, sigma x by 2 plus sigma y by 2. So that is sigma x plus sigma y by 2. Now sigma x by 2 into cos 2 theta minus sigma y by 2 cos 2 theta. So cos 2 theta is common. You get sigma x minus sigma y by 2 into cos 2 theta. And 2 cos theta sin theta you can replace as sin 2 theta. So tau xy sin 2 theta. So you'll get the normal stress as sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. That will give the normal stress on a plane inclined theta from the vertical when it is subjected to two-dimensional state of stress. Now to find out the shear stress along the plane, you have to resolve the forces along the plane. Okay, we have to resolve the forces along the plane. Now let us sum up the forces along the plane and equate to 0. Since element is in equilibrium, the summation in any direction has to be equal to 0. So along the plane or tangential to the plane, I'll sum up the forces and equate to 0. Now I'll take upward as positive, downward as negative. So this force is acting upward, tau EC. Tau EC I written, it's upward, so positive. Now the vertical forces along the plane, if you resolve, that is in giving cos theta. Since the vertical is making theta from the plane, this tangential plane, vertical forces component is cos theta. Horizontal force, its component is sin theta. Horizontal force, this angle is 90 minus theta, or the component will be sin theta, cos 90 minus theta or sin theta. So vertical force sigma y EB, this is a vertical force into the angle is theta, so cos theta, component along the plane is cos theta, sigma y EB cos theta. Now vertical force I will take tau xy BC, again cos theta component, so both acting upward and the component will be acting upward, so in this direction. But these forces, horizontal forces, which is acting rightward, its component along the plane will be downward. Now you take sigma x bc. Sigma x bc is acting like this. Its components, normal component will go upward, but component along the plane will come downward. So you have to take negative. This tangential component you should take negative. So sigma x bc is acting rightward, its component along the plane will come downward. So sigma x bc into sin theta, but it's negative. Similarly, this also, the component, tangential component will come downward. So minus tau xy eb, again the component is sin theta. So this summation is equal to 0. Now take all this to the right hand side, keeping tau EC on the left hand side. So tau EC is equal to, I'll take this, this I'll write first. So sigma x bc sin theta plus tau xy, this negative components I have written first, okay. Sigma x bc sin theta plus tau xy eb sin theta minus sigma y eb cos theta minus tau xy bc cos theta. Now I'll divide the entire equation by EC. You get sigma x into BC by EC sin theta plus tau xy EB by EC sin theta minus sigma y EB by EC cos theta minus tau xy BC by EC cos theta. Now again you can replace BC by EC as cos theta and EB by EC as sin theta. Same equation I have written here, replacing BC by EC by cos theta, you get sigma x cos theta sin theta and tau xy sin theta into sin theta, sin square theta minus sigma y sin theta cos theta minus tau xy, BC by EC is cos theta, so cos square theta, tau xy cos square theta. Now this term and this term, you have cos theta sin theta common. Cos theta sin theta I will take outside into sigma x minus sigma y, and this two terms you can combine. So minus tau xy I will take outside, okay. So you will get minus tau xy if you take outside, cos square theta minus sin square theta. Now cos theta sin theta is sin 2 theta by 2. So this sin 2 theta by 2 and cos square theta minus sin square theta is cos 2 theta. So minus tau xy cos 2 theta. So this you can write it as sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. So shear stress tau is equal to sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. So this is shear stress on that particular plane. So when you take any section plane, you can find out the normal stress and shear stress acting on that plane. So normal stress we have seen, that is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. This gives the normal stress on a plane inclined theta from the vertical, and shear stress is sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. So this way, when a body is subjected to two-dimensional state of stress, that is plane stress, we can find out the normal and shear stress acting on any plane inclined theta from the vertical. So any inclination you take, you can find out the normal stress and shear stress. That's all for today. Thank you for watching.